All right, so I just wanted to kind of go over a few things in chapter 14 tonight. So we're going to be talking about crying in the mud. Did my pen not work? One moment, please. Dang gummit. Oh, here's the other one right here. I knew it was here somewhere. All right, so we're going to be dealing with, yay, kilojoules. Kilojoules. Kilojoules, attaboy. And of course, that's thousands of joules. We're going to be dealing with most of what we do. Okay. Joules is not very much when it comes to heat. It's just not that much. So we use a lot of kilojoules. Okay. Now, in the day, what we would say is that 1 kilocalorie, which is what we typically refer to a calorie as, 1 kilocalorie is equal to 4,185 joules. And that was a big deal. But now, in the course of this class, we're going to use a kilojoule. So, we're going to speak specifically of how many kilojoules, in other words, how much heat would it take to raise the temp of steel or water or whatever. Water, I don't know, 10 degrees or something like that. Okay. That's the sort of thing we're going to be talking about. Or, hey, listen, if I dumped this piece of steel into some water, how much would the water come out? Obviously, they're going to come to equilibrium. What would that equilibrium point be? That's the kind of things we're going to be looking at a ton. So if you recall, obviously, we talked about joules when we talked about kinetic energy and things like that. And so once we have kinetic energy, like Groom, are we going to use friction to stop our cars? We are. Hey, they're going to heat up our brakes? Duh. And so, of course, that's going to come up into this chapter as well. But we're going to talk specifically today I want to talk about specific heat capacity. And we're going to talk about it in terms of really just specific heat. Now, the actual word is, or the actual thing is specific heat capacity, but we're going to say the specific heat. And so, specifically, what we're going to talk about is the change in temperature. Q, God bless. Q, the amount of heat energy, is equal to mc delta T. And so this is the mass of the stuff in question. This is the specific heat of the stuff in question. And this is the change in temp. Okay, that's the specific pieces that we're going to be discussing. Okay, and that's what I want to focus on with you on tonight during our little thing here. Okay, so so as I say, specific, there it is. Now, for instance, so specific heat is specifically how much heat is required to raise the temp of 1 kilogram of something 1 degree Celsius. Okay, that's just it. That's all it is. So for water's huge. It's 4.19 kilojoules, and these are always measured in degree per kilogram degree Celsius. Okay, that's what it's measured in. But 4.19 kilojoules, that is a butt ton. And so what we normally say is we say water has a very high thermal inertia. If it's cold, it wants to stay cold. If it's hot, it wants to stay hot. And the idea being is that it doesn't change, willy-nilly. If you leave a piece of a spoon on the sidewalk on a hot day, man, sucker's hotter than a pistol in just a couple seconds. And if you put it outside in the snow, it's ice cold in just a couple seconds. Because why? It doesn't take a lot of heat for it to change temperature a great deal. Okay. And so if like steel, don't quote me on this. Well, you can quote me. I'm going to tell you exactly what it is. By God, it's right there. Steel is like 0.46. So it's almost 10 times less heat energy it takes to raise it 1 degree or lower it 1 degree Celsius. Now, remember that the idea here being is that we're going to be given something, and so if we want to cool it down, we have to remove the heat from it. If we want to heat it up, we have to put heat into it, obviously. Yes, that's the game. And so if you have this piece of steel here and you'd like it to be, let's say it weighs 2 kilograms, nice, and it's currently at 30 degrees C, and we'd like to raise it to 300 degrees C, nice. How much energy is that going to take? Well, I don't know, but wait, I can figure it out. So Q is M times C for steel is 0.46. Just looked it up. Right. Times the change in temp, which is 270. Notice that's positive 270 because, we're going that direction. We're putting it in versus if I wanted to cool it down, I have to remove this much heat, and it would be negative. So you get 248 kilojoules would have to be added to raise it that much to that temperature. Okay. Let's say you had some water and you had 4 liters of water. Remember, 4 liters is equal to 4 kilograms. That's one thing that they got right about. Other than that, I don't like the metric system, but whatever. There it is. Now, it is currently at 6 degrees C. We would like to raise it to 30 degrees C. That's hot. And so, literally hot. It's actually tepid. But anyway, here we go. So, Q is equal to M for C is 4.19. And then times 24. Remember, this will be in kilojoules. 4 times 4.19 times 24 is 402 kilojoules. Nice. Piece of cake, baby. Piece of cake, huh? Piece of cake. Nice. Now, Groom, what would happen if we took a hot piece of steel and dropped it into this bucket of water? Well, first of all, obviously, it's going to cool the steel off. It's going to warm the water up. So how much steel are you going to throw in? I'm going to throw in 1/2 kilogram of steel. 1/2 kilogram steel. This is 3 liters of water. Nice. The water was initially at 10 degrees C. This sucker here was at 200 degrees C. What is the final resting temp of the water? Bro, I don't know, but here's what I do know. The amount of energy gained by the water is equal to the amount of energy lost by the steel, yes? So M times C times delta T. Now you're like, Groom, what was it? Well, it's 10 minus the final, yes? Is equal to, and on the other side it is M, so 0.5 times 0.46 times 200 minus, oh geez, Groom, the same final temperature. By God, they do. You're right. T sub F, T sub F. Wow, that's pretty killer. I know, right? So if watch me pop this up. 3 times 4.19. All right, so this times 10 is 125.7. Minus 12.57 T final is equal to 0.5 times 0.46 times 200 was 46 minus 0.23 TF. So I'm going to solve. So 125.7 minus 46 is 79.7 is equal to, let's plus that. So 12.5 minus 0.23 is 12.27 TF. And if you divide 12.27, and so you get, oops, 79.7 divided by, and you get about 6.49 degrees. What? Now, see, once in a while you kind of screw up, Groom. See? Nice. So, did I make a boo-boo? I did. Let's see if I can tackle it where I made that boo-boo at. One moment, please. Sorry, I remember what I did wrong now. Check me on this. It's TF minus 10. So this should be negative, and that should be positive. TF minus 200. There's the initials, in other words. You with me? I think we got her this time, baby. Something's still screwy. Something is still screwy. And check me. I know what happened here. Sorry, this is the amount lost. This has to be negative on this side. I think that's what's going to get it to us. Here we go. Groom will get there eventually, sir. Let's try this again. So if I plus that over to here. Right. Boop, doop. All right, so let's do this. So I'm going to take his calculator. Let's try this again. What we're going to do is we're going to go 0.46 plus 12.5. That, and then we're going to take, and we're going to do 46 plus 125. And we're going to take that guy divided by that guy. And 13.1 degrees. There we go, 13.1 degrees. So that's the final temperature for both of them. Notice the water didn't move a whole lot. Okay, clearly the water get warmer, but not by much. Again, it takes 10 times as much heat to change the temperature of water than it does to change the temperature of steel, roughly speaking. Okay, that's a lot. Okay, so that means the steel cools down rapidly and nothing much happens to your water. By the way, this is what happens. This is what happens in the summertime. You're like, Groom, that pool in our backyard is so cold. And it's cold. Even at noon, it's still cold. And by about 6 o'clock at night, boy, it's starting to get a little bit warm. It's starting to get warm. And then all night long, it's pretty dadgum warm until it cools off, midnight, whenever. Okay, great. Why? It took forever to heat up. And once it did, it doesn't want to change. Okay? 9 o'clock, you step on the asphalt, it's hotter than a $2 pistol. Right? And you're like, well, how did it get so hot? Well, obviously, that's a tiny specific heat, so it shoots up temperature-wise. And then, as soon as the heat goes off, the sun goes off of it, man, it cools right down. Okay? Right back off of this thing. Okay? That's a pretty big deal. Now, this is what we're focusing on today, specific heat. Okay? Now, let's say you had some, I don't know, piece of metal, right? And you're like, well, again, let's say it was something like, I don't know, brass. Sure, brass. Got brass in pocket. Nope, can't use brass. I don't have it. How about silver? Silver has a specific heat of 0.23. It heats up twice as fast as steel does. Whoa. So if I have a piece of silver that is like, I don't know, 10 kilograms, that's a monster. And it is current, I need to get, and if I let me do that. If I'm going to change it up a little bit here, let's say impart 1200 kilojoules. What will the final temp be? I don't know. 1200 is equal to mass times C times delta T. Question, what is the temp right now? Currently, the temperature initial is 10 degrees C, baby. Now, Groom will just normally solve for this and then plus it onto this or minus it, whichever the case may be. You with me, babe? And so 10 times that is 2.3, so 1200 divided by 2.3 is 521 degrees change in temp. From what? Well, from 10. So we are currently then going to be at 531 degrees C. Yay! And we can play this game until we're blue in the face. Specific heat is actually quite easy to do. Okay? All right. Now, the next thing I want to talk about a little bit tonight is the latent heat of fusion and vaporization. If you like ice cubes, which, let's be honest, who doesn't? If you like air conditioning, which, let's be honest, again, who doesn't? They both rely on this concept. It's huge. Okay, so let's say I took some water in a little tray here. It's a little tray. It's like a quarter of a kilogram. Nice. And it's currently at, I don't know, 5 degrees C. I would like to freeze it. I want to freeze it. Okay. Well, first, I have to get to 0. That is the freezing point, right? So first things first. So Q equals MC delta T. And so that's 5. -5 technically. So you look at that, you're like, well, how much energy do I need to pull out of it? 0.25 times 4.19 times 0.5. Or no, -5, sorry. So I need to pull out -5.23 kilojoules. All right, cool. Then it has to freeze. Here's the problem. To get it to freeze, I have to remove a ton more out to get to freeze. In other words, until I pull the next amount of energy out, it's going to stay in a liquid form at 0 degrees C. That is, I have to pull a ton more out to get it over that fusion, that change of state between liquid and a solid. And so for the specific, or the latent heat of fusion for water, it is 335 kilojoules per kilogram. 335 kilojoules per kilogram. Now notice, it is not per degree Celsius because it does not change temperature. It goes from 0 degree water to 0 degree ice. Okay? And so I had a quarter of a kilogram. So I'm going to take 0.25 times 335 and I get, so 83, that's -83. -83.7. I need to pull that much out plus the 5.23 initially I had. I need to pull out, damn it, dumb hippie. I need to pull out 89 roughly kilojoules to get it down to 0 and then freeze it. Okay. What if I wanted to boil some water? That's a good question, sir. Okay, first of all, let's just worry about just the pan right now, okay? I'm just worry about just the water right now. So I have 1 kilogram of water. Water at, well, it's currently at 22 degrees C. I need to get to 100, obviously. Oops, 1,000 degrees. That'd be a good trick. So it's going to be Q equals MC delta T. I need to put in that much heat. That's just for the water. So 1 times 4.19 times 78. Now that's just for the water. So 326 kilojoules just to get the water up there. But what about the pan, Groom? It's 1 kilogram of aluminium. Dude, you shouldn't cook with aluminium, but okay, let's do it. So that is going to be 1 times, hey, the specific heat for aluminium is, specific heat for aluminium is 0.92. So I need to get the pan and the water both warmed up. So I need to put this much in. So that's 397 kilojoules roughly, just to get up to 100 degrees. Now I need to boil it. Now here's the thing. To get from liquid to vapor, right, to gas, this is what we need to add the latent heat of vaporization. Okay, that's the hidden heat of vaporization. And for water, it is 2,260 kilojoules per kilogram. So to boil all of this water off, all of it is going to take, I need to get to this, plus, so 397, plus I have a whole kilogram of water I need to boil off. I need to add that much more energy. So 397 plus 2260, 2,657 kilojoules. Okay. Now, Groom, are we going to figure out how efficient this stove is? Yeah, soon. Not now, but yeah, soon. Because, well, Groom, it's putting out this many kilowatts. But it had to take like 7 hours. Dude, I know. Whoa, that's not very efficient. Yeah, I know. We'll talk more about that next time. But for today, you're going to be doing problems involving the latent heat of fusion and specific heat. Okay, and we'll pick that up next time.